Now we will look at how to reduce a higher order equation to a first order equation system. Because when you reduce a higher order to a lower order, as a trade-off, we have more equations. For example, here is a second order, right? X, the second order derivative is equal to certain expression that involves probably the t variable and x and its first order derivative. So this is an equation of x, but it's a second order equation because the highest order derivative appearing in this equation is second order. So we hope to reduce it to the first order. So we introduce, for example, let's call this as a one function and call this first derivative as another function. So of course, there's no need, right, to rename the function x into u1, right? You can keep x as is, right? You don't have to find another name. But the reason I choose to use u1 is to have a consistent notation. So do a little change to this name, the x. So I call it u1. X derivative, I call it u2. So as soon as we have these two, these are functions, and then the second order derivative of x will be u2 derivative. So it becomes first order derivative because we have introduced we call this a function u2. So second order derivative of x becomes first derivative of u2. So immediately this equation, the originally given second order becomes first order equation. So then we can continue to write as f and t as an expression of t, x, let's call it u1, u2. So now we have reduced the order to first order. But this equation, what is u2, right? We know the u1, u2 satisfies, actually u1's derivative is u2. So that's because of this. So u1's derivative is u2. Now we have written the original problem into a system of two equations. So you see, reduce the second order to first order, we get two equations, right? The original problem of one equation has become a system of two equations. But as you can imagine, if you want to reduce third order, a single equation into first order system of equations, you will get three equations of first order. So similarly, so you can predict if you have a fifth order single equation to reduce to first order, you will get 5 of the first order equations in the system. So now we get first order. However, we also hope that we have first order autonomous system. So if our original problem is non-autonomous, here, like right now, we still have the right-hand side explicitly depending on t. So we want to make that t variable disappear. So let's further reduce it. So step one, we already reduced it to first order, but let's continue to make it into first order autonomous system. So the only thing is that t, so we want to introduce another function, let's essentially the t, and we name this one as u naught. So u naught, if you take a derivative of u naught with respect to t, it's going to be 1. But the other two equations we keep as is. So the u1 derivative is u2. u2's derivative is f, the expression that depends on t, which is u naught, u1, and u2. So now this new system, the t disappeared. So it is autonomous. So you see, step one, we reduce it to first order. We get more equations. Step two, we make it into an autonomous first order system. Yeah, so this system, if you write it in the vector form, so we have, we have u naught, u1, u2. So this vector value function's derivative equals the vector field is 1, u2, and this expression of u naught, u1, u2. So u naught, u1, u2. Okay, so the right-hand side depends on this unknown function, right? This part only. Yeah, t does not appear at all on the right-hand side. Now it is autonomous. So now this is just one example to show how generally we can reduce the order and how to make it into autonomous first order. So from this example, you can quickly apply the technique and reduce even a case order. Let's assume we have a case order and we hope to reduce this single equation of case order. So this highest order derivative is isolated and it is on one side, and the rest is on the other side. So this is an expression, a certain expression called f that can depend on t and the function x first derivative, all the way up to the k minus 1's derivative of x. So how do we reduce this one equation into k equations? Okay, very similar. We just yeah, so let's first we name, just think this is our u1, this is u2, right? All the way this last one will be uk. And we also want to make it autonomous. So this t will be u naught. So with that notation, it's just a little bit convenient notation. Then we can rewrite. We can see that u naught, the derivative is 1. u1 derivative, u1's derivative with respect to t is u2. u2 derivative will be u3, etc. So we continue in this fashion. We can see uk's derivative because our uk is the k minus 1 derivative of x. So if you take a derivative of this uk, then you get the kth order derivative of x. So that will be f at, now with our new notations, so the t is called u naught, x is u1, u2, all the way to uk. So now we got a system of k plus 1 equations. So as you can see, to reduce a kth order to the first order, right, we will have, so this one single equation of kth order will become k of the first order equations. So you will have more equations. But to make it into autonomous, so there is another equation. So we will have a total of k plus 1 equations. So with that many equations, but this is a system of first order and also autonomous. So that there's some nice feature. We can simply write the derivative of the unknown function will be this in the vector form. This is the vector valued curve, right, to be looked after. So we are looking for such a solution in the vector form. So the right-hand side is the vector field that involves only this vector. So the right-hand side does not depend on t explicitly. So we just write it's the last equation will be u naught, u1, u2, uk. Okay, so this is the general strategy to reduce a kth order equation, a general equation in normal form, into a first order autonomous system of equations. Now, a question I want to give you to think about is, suppose I have a kth order equation that is not in a normal form. You see, the kth order equation that is in normal form, it is this form, where the highest order derivative is isolated. It is on left side, right? It is written in terms of lower order derivatives or the unknown function x or t. So this x, okay, this is the case order equation in normal form. So now let's look at an equation that is case order. So the highest order derivative is still k, and then the next highest order derivative is k minus 1 with the coefficient, let's call it a1, and call it a1. And then there's a coefficient y that is so in this pattern. So actually a1 all the way to ak can be variable coefficients. They don't have to be constant coefficients. So a1 can depend on t, ak can depend on t. So you have a so once we have all the so suppose I have an equation that is of the case order. So this equation, certainly if I move everything to the right-hand side, then you have the normal form of a case order equation. So it's a really similar situation you can get immediately. So what is the capital F? Right, so that capital F will be explicitly, so all these terms, it's so you can think of this specific case when you have a case order equation such as this one. So if you apply our previous method, you can, if you want, to write it into the normal equation form. So let's isolate the highest order derivative, which is a case order derivative, and then keep the rest. And just move each one of the terms to the right-hand side. Yeah, next term will be k minus 2. And then every term until the last term, which is ak of t times y, the function. So that is an expression that depends on t, the t. So it's definitely not, it's non-autonomous, right? Because it has the t, and also it has the depend on y and up to all the way k minus 1 derivative of y. So yeah, so that is our capital F, this part. That's the capital F, the expression. So think about this case, then how do you reduce it? Then after you reduce, we can get the first order. So just quickly think of the reduction. So we need to introduce the new names. So which one, suppose if you call this one as a U1, for example, if we call it U1, the y first derivative will be U2, and then this one all the way to this one will be UK, right? And then you introduce, and this will be UK's first derivative. So then we have already reduced the case order, higher order derivative equation into first order. So let's go ahead and do the reduction. So the reduction will, this case order of y becomes uk. Yeah, so actually we need a little bit more room. So let's move it up. So this uk first derivative, which is equal to negative a1 t uk minus a2 uk minus 1, and then minus all the way to ak u1. But don't forget this each a is a time-dependent coefficient. So after we reduce to first order, we need to also indicate the relationship. This u1, you see u1's derivative is u2. u2's derivative is u3. That will continue until, right, until u k minus 1's derivative is uk. uk's derivative is this long one. So let's give a little. uk's derivative, the last one, is this one. So still, this is, although it is a first order system, right, from a single equation of case order, it has become k equations of the first order. But it is not autonomous. Why it is not autonomous? Because the coefficients are the functions of t. The t variable explicitly, yeah, appears in the vector field. So in order to make it autonomous, let's define a new function. For example, let's call it u0. u0 derivative is 1. u0 is actually the t. So then we can replace all whatever t on the right-hand side with u0. So now this will become a u0. So each coefficient, wherever you see t, it will be expression of u0. So now we have a system of k plus 1 equations. K plus 1 equations. And first order autonomous. Yeah. So if your goal, depending on your goal, if you only want to reduce it to first order, then you don't need to do this, right? You just simply get first order. If you want to get it a first order and autonomous system, then you can do more to reduce the system into that form. So depending on your goal for the problem. So let's think if we only get to the suppose first order. So from here, if we do not introduce one additional equation like this one, then you can just consider u1 derivative is u2, u2 derivative is u3, and all the way to the uk minus 1's derivative is uk. uk's derivative is the last one. Negative a1. So if I still keep the t as as like a variable coefficient, right? Each coefficient could be a coefficient depending on t. So we can still keep that t. That means if we just reduce it to the first order, it doesn't matter if we keep it as a non-autonomous. So then we can study this form. AK of t u1. So compare. So this one compared to the previous one, it's just we get a first order. So the difference is they're both first order, but the set of purple equations is first order, but still a time-dependent vector field, right? So this, you see the time-dependent. It's non-autonomous. This equation, the system is actually a linear system because we can write this system into a vector equals a matrix times that vector. So you can write it into derivative of the vector u1, u2, uk, and coefficient. So you see coefficient of u1 is 0, right, for the first equation. Coefficient of u2 is 1. And coefficient of u, so in the first equation, so you can see the coefficient of u2 is 1, and coefficient for u1, u2, all the way to uk will be 0. So we know in the first equation, we have zeros for all the other uk. u1 through uk, only the coefficient of u2 is 1, right, for the first equation. The second equation, you see the coefficient of u3 is 0. So you have only this entry's coefficient of u3 is 1 for the second equation. So the second row has only the entry 1 here. Everything else will be 0. So we will get zeros for the rest of this row. And then similarly, then you see the pattern will be continuing, and then you get 0, 0, all the way to 0. Yeah, still. And then this is a 1. This is a 0. So you see the pattern is this diagonal of 1s. Yeah, so I want to make it a little neat. So here it's something 0. So it's just the diagonal of 1s for this portion. And then you have, again, the last equation. So what is the last equation? Coefficient of u1, right? It is negative ak. So we need to put here negative AK as a function of t, and then negative, etc. So all the way. Then for the coefficient of UK is negative A1 as a function of t. So this matrix is the coefficient matrix. We can make it to, just so you can see this is a linear system. Yeah, non-autonomous, a linear system. But when you make it into autonomous, it's no longer linear, right? Because you see this times this, so the u, it's not necessarily linear. So sometimes you make it a linear system. For this case, you get a linear, although it is not autonomous. But when you try to make it for first order also autonomous, but it's not a linear system. So we just see the difference when you try to reduce to what level and then what is the feature of the new system. Okay.